When you boil down machine learning to its core mechanics, training an AI is essentially an exercise in finding the bottom. We can visualize a line of code actively learning as a single point of light, navigating a physical space. Every parameter in a neural network, every weight and bias, adds a new spatial dimension. Plot all the possible configurations against how many mistakes the AI makes, and you generate a topographic map of error. The higher the altitude, the more mistakes the model makes. The entire goal of optimization is to reduce that error. The algorithm creates a simulated gravity, pulling the AI downward into the valleys of this landscape until it finds the lowest possible altitude. This works because of what data scientists call the manifold hypothesis. It suggests that even the most chaotic, high-dimensional real-world data, like millions of pixels in a photograph, maps neatly onto a simpler, underlying geometric structure. But this structure is invisible to the AI at the start. The network begins on a blind pathfinding mission, navigating thousands of parameters by feeling its way through the landscape one step at a time. The standard tool for this descent is stochastic gradient descent. You can think of it as a microscopic point particle that blindly follows the steepest slope straight down into the canyon. The danger here is that the loss landscape is rarely a smooth bowl. It is highly non-convex. The terrain is littered with local traps, small, jagged pits that look like the absolute bottom, but aren't. The most treacherous of these traps is known as a sharp minimum. If you look at a cross-section of the terrain, a standard flat minimum looks like a wide, forgiving U-shaped valley. A sharp minimum is a deep, incredibly narrow V-shaped gorge. If the AI's algorithm falls into that tight V-shape, it achieves a low error rate on its training data. It memorizes the specific examples you fed it perfectly. But because the valley is so narrow, even a tiny change in the data, like seeing a real-world image for the first time, pushes the AI straight up the steep canyon wall, causing a massive spike in errors. Simply finding the lowest altitude is a liability if the terrain around it is so steep that the model's logic becomes brittle. To solve this, researchers are turning to topological data analysis. Instead of just calculating the immediate steepness of the ground beneath the AI, this approach forces the algorithm to evaluate the overall shape of the valley it occupies. The key metric here is escapability. If an algorithm gets stuck in a trap, we want to know the exact mathematical height it has to climb in order to break out and find a better, wider valley. A loss barcode records the exact error the AI must accept to escape a local minimum. Longer lines indicate a deep pit, requiring massive computational energy to escape. Conversely, a flat valley produces short lines, meaning the AI easily rolls out without error spikes. To build robust models, we must design optimizers that don't just settle for the first pit they fall into, but actively bypass deep traps to seek out these flat, easily escapable regions. One way to do this is by changing the physical nature of the AI agent itself. We can upgrade the standard point particle algorithm to something researchers call a rolling ball optimizer, expanding the agent into a sphere with a finite radius. The sphere's bulk prevents it from dropping into narrow crevices. It glides over the jagged spikes and traps, ironing the terrain into a smooth dune. This ironing property dictates that the sharp minima are strictly unreachable. The sphere's radius physically prevents it from engaging with microscopic relics, forcing it to respond only to the macro structures of the environment. By tuning the physical scale of the optimizer, we strip away the chaotic noise. The AI ignores the traps and safely homes in on the true underlying data patterns. There's a catch to visualizing these landscapes. Our brains only process 2 or 3 spatial dimensions, but neural networks operate across millions of parameters simultaneously. To map this accurately, developers use a tool called Landscaper. It projects the landscape using Hessian eigenvectors, a mathematical technique that identifies the specific dimensional directions where the AI's error fluctuates the most. When compressed to a 3D map, we see phantom barriers. The agent hits a steep wall and looks stuck, but expanding into 5 dimensions reveals the wall was just a narrow slice. In higher dimensional space, wide open pathways wrap right around the obstacle. To quantify this global connectivity without getting tricked by 3D illusions, scientists use a metric called saddle minimum average distance, or SMAD. Instead of measuring local steepness, SMAD calculates the roughness and connectivity of the entire basin. This image shows a complex molecular structure an AI model is predicting. In complex tasks like this, local curvature metrics misrepresent capability. It's the global topological smoothness, measured by SMAD, that accurately predicts if a model will succeed on unseen data. Robust generalization is a product of this global connectivity. By bypassing brittle local traps, the AI settles into a landscape where solutions remain stable across different datasets, flowing through a network of interconnected valleys.